In this section, we want to talk about complex numbers. Complex numbers are the numbers that have imaginary number as part of their. What are the imaginary numbers? Imaginary numbers are negative numbers under the square root, because we know when we talk about real numbers, there is no negatives under the square root. If we have a square root, we always said that we cannot have negative under the radical. Now, if we have a negative under the radical, it's called imaginary number. So that's why we called the square root of -1 I. And that is the imaginary number that we use for complex numbers. If I is the square root of -1, and if we square both sides, we get I squared, which is equal to, so I squared, it means I times I, which is root -1 times root -1, and that's square root of -1 to the second power. Power and root cancel each other, so the answer is -1. So I is the imaginary unit of any complex number, and we know that the I squared is always equal to -1. And if we have a number in forms of a plus bi, which a is a real number, and b is the imaginary, bi is the imaginary part, we call this a complex number. And the standard form of writing any complex number is a plus bi, which means we write the real number first and then plus or minus bi, which is the imaginary part. Like 2 plus 3i, for example. So if we have a complex number written in forms of, for example, 2i plus 1, we always need to change it into the standard form, which is 1 plus 2i. So the real part, which has no I, must come first, and then the imaginary parts. Operations on complex number is exactly the same as binomials like a plus bx. How we add binomials, how we subtract, how we multiply, we do exactly the same with a complex number. For example, if we have 2 plus 3x, and they ask you to multiply it by 2, what do? You just distribute the 2, and you say 4 plus 6x. And that's exactly the same as if we have 2 plus 3i, which is a complex number, and if they ask you to multiply by 2, you distribute the 2 and you say that's 4 plus 6i. For adding and subtracting complex numbers, we always add or subtract like terms, and like terms here are real parts adding together, imaginary parts adding together. And the same for subtraction. We subtract real parts, which is a and c, and so we say a minus c, and we subtract imaginary parts, which are bi and di, and if we subtract them, it's b minus di. So for add or subtract, we just add real parts together and imaginary parts together. Add or subtract. For example, we want to add or subtract these complex number. In part A, we have two complex numbers that we want to add them. So as we mentioned, we need to add real parts together and imaginary parts together, which means we need to add 5 and 3 together, -2i and +3i together. But something that we need to know, for add or subtract, we always have to drop the parentheses first. And when you want to drop the parentheses, you need to make sure that there is no number in front of the parenthesis. So right now, when you look at these two parentheses, you see there is no number or sign in front of the parentheses. So you can easily drop the parenthesis and write it as a 5 minus 2i and 3 plus 3i. And then add real part, 5 plus 3, which is 8, -2i plus 3i, which is +1i. And we do the same for subtraction. Subtract the real parts, 2 minus 12, which is -10, subtract the imaginary part, which is 6i minus negative I. So remember that we need to distribute the negative. So which gives me positive I. So if you drop the parenthesis, the first parenthesis doesn't have any numbers in front, so we say 2 plus 6i, but the second parenthesis has a negative, so you distribute the negative, so you get negative 12 plus I. Now you add or subtract real parts, add or subtract imaginary, based on their sign. If both are positive or both are negatives, we add them. If one is positive, one is negative, we subtract them. So we have negative 10 plus 7i as a final answer. So next example, it says find the product. We want to multiply complex numbers. We do the same as the binomials. So to multiply one term to two term, we need to use a distributive property. We need to distribute 7i by the parenthesis, which means multiply 7i by 2, which is 14i, and distribute 7i by negative 9i, which is negative 63i squared. So remember, when you multiply I times I, it gives you I squared. Now, you know the I squared is always equal to negative 1, so you need to replace the I squared by negative 1. And if you replace I squared by negative 1, negative 63 times negative 1 gives you positive 63. Now your answer is 14i plus 63. But that's not the standard form of the complex number, because in standard form, the real part with 63 must come first and then 14i. So we just reorder the number and we write it as a 63 plus 14i. In part B, we have two parentheses, two complex numbers. We want to multiply them. Like binomials, we need to multiply everything from the first parenthesis by everything from in the second parenthesis. Multiply 5 by 6, 5 by negative 7i. Multiply 4i by 6 and 4i by negative 7i. So 5 times 6 is 30. 5 times negative 7i is negative 35i. 4i times 6 is positive 24i, and 4i times negative 7i, it's negative 28i squared. Again, every time we see I squared, we should replace it with negative 1. And if I replace this by negative 1, we get negative 28 times negative 1, which is positive 28. And positive 28 and positive 30 are real parts, are like terms, we can add them together and it gives me 58. And these two also are like terms because they both have I, so we can add or subtract them. And negative 35 plus 24 is negative 11i. So that's the final answer. We combine the like terms. Conjugate of a complex number. Conjugate of a complex number, that's exactly the same as the conjugate as we talked about for rationalizing radicals. So if you remember, for rationalizing radicals, that they had two terms on the denominator, like 2 plus root 3. For rationalizing these radicals, we need to multiply by the conjugate. Conjugates are exactly same number, 2 and root 3 are the same, but the sign in between will change from positive to negative or from negative to positive. So 2 minus root 3 is a conjugate for 2 plus root 3. And we need the conjugate for division. If I want to divide two complex numbers, like dividing two radical expression, I need to multiply by the conjugate, like exactly the same as what we did for rationalizing. Because if I multiply every complex number by its conjugate, you don't have any I for the answer. Because you just, when you multiply one by one, you get a times a, which is a squared, a times negative bi, positive bi times a, and positive bi times negative bi, which is negative b squared I squared. These two are like term and cancel each other. I know the I square is -1, and if I multiply negative b square by -1, it gives me positive b square. So the final answer is a square plus b square. And there is no more I or imaginary parts. So just remember the conjugate that has the exactly same number, just the sign between the terms will be changed. And why do we need conjugate? For dividing, for division. If I want to divide two complex number, I'm going to use conjugate. For example, we want to divide and express this result in a standard form. We want to divide two complex number. So what do we do for dividing? Multiply by the conjugate of the denominator. So the denominator is 4 minus I. And the conjugate of the denominator is 4 plus I. So I need to multiply both of the numerators and denominator by 4 plus I. Because if I multiply the denominators 4 minus I and 4 plus I, it's like a square plus b square, which is 4 square plus I square. And I square is -1, so it's 16 plus 1 plus -1, which is 15. So if we multiply both top and the bottom with the complex conjugate of the denominator, which is 4 plus I, and multiply the parentheses on top one by one, and multiply the denominators, we get 16 minus -1, which is, +1, and that's 17, and we combine the like terms on top, we get 16 plus 21I, and we can, since right now there is no more I on the denominator, we can divide each term on the top by 17, separate the fractions, and rewrite it as a 16 over 17 plus 21I over 17. Now we have a complex number in a standard form. Next example, we want to divide these complex numbers. Again, we need to multiply by the complex conjugate of the denominator. On the denominator, I have -2 and I have I. But if there is negative in between, I change it to positive. I only change this sign, not the change of, don't change the sign of everything. -2 stay the same, still is -2. The only thing that changed for the conjugate is the sign that's between the two terms. If it's negative, you change it to positive. So we will have -2 plus I on top as well. Now it's time to multiply the tops and the denominators. You can multiply one by one, or if it's easier, you can also use the box method for multiplying. So we have two terms on top, which is 7 and -3I. That's the first parenthesis. And two terms on the left side, which is -2 and +I, the second parenthesis, and then multiply it in the box. -2 times 7, -2 times -3I, I times -3I. Oh, sorry, here. And I times 7I, which is I times 7, which is 7I. We can combine the like term. 7I plus 6I is 13I. We have a -14, and we also have a -3I square. I square is -1. If I multiply -1 by -3, it gives me +3. I bring down the rest. Now I see that the -14 and +3 are like terms. I can combine them. So I get -11 plus 13I on numerator. You have to do the same for denominator. I have to multiply -2 minus I by -2 plus I. So if I multiply everything, I have -2 times -2, which is +4, -2 times I, which is -2I, negative I times -2, which is +2I, and negative I times positive I, it's negative I squared. Combine like terms, these two cancel each other. I know I squared is -1, and negative times a negative is positive, so it's 4 plus 1, which is 5. So the answer for denominator is 5. Now, since we have only one term on the denominator, I can split the fractions and just rewrite as a -11/5, which is my real part, and 13/5I, which is my imaginary part. And that's the final answer. The principal square root of a negative number. So we always in a real number said there is no way that we can keep negative under the radical. And every time before this section, we had a negative under the radical, we said there is no solution because there is no actually real solution. But we may have imaginary solutions because we learned that the square root of -1 is I. So now if in any problems, I have a negative number under the radical, for example, I have a radical -b, I can rewrite this one as a -1 times b. If I keep them under the separate radicals, I know that the square root of -1 is I, so the answer is I square root of b. And if b is a perfect square, we can take the root. If it's not, we can keep it with the radical. Depends on the number. And we use this rule to simplify some numbers. For example, what is the square root of -121? So -121 is -1 times 121. Since there is a multiplication between them, you can separate them under the and rewrite it as a separate radicals. Now we say the square root of 121 is 11, and the square root of -1 is I, and 11 times I is just 11I. Square root of 80, that means that's a square root of -80, which is -1 times 80. That means it's the square root of -1 times the square root of 80. Square root of -1 is I, and now what's the square root of 80? So if you wanted to simplify 80, you know that the 80 is 8 times 10, or 4 times 20. And 20 is also 4 times 5. And I know that 4 is a perfect square, I can bring it out. So square root of 4 times the square root of 4 times the square root of 5, which is 2 times 2 times root 5. And 2 times 2 is 4 square root of 5. Now I need to multiply 4 root 5 by I, which is 4I root 5. So it's better we keep the number in before I, but the radicals after I. Next part C. We want to simplify this one and find the answer. So first of all, we need to simplify under the radical. And if I want to simplify based on the order operation, I know 7 squared is 49. I know that 4 times 5 times 4 is 80. So it's square root of 49 minus 80, which is -31. And you can rewrite this one as the square root of -1 times the square root of 31. But the 31, it's not a perfect square, and we can't simplify that. So we have to keep it as a radical. but the square root of negative 1 is I. So the final answer is I square root of 31. Let's simplify this expression now. So to simplify this expression, in part A, we need to simplify the radicals first, each of the radicals separately. A square root of negative 27, which means negative 1 times 27, that's the square root of negative 1 times the square root of 27. A square root of negative 1 is I, but now we just need to simplify the square root of 27. I know that the 27 is 9 times 3. So the square root of 27 is the square root of 9 times the square root of 3. And the square root of 9 is just 3 without any square root, but this one stay the same. So we have I times 3 root 3, which is 3I root 3. We do the same for the square root of negative 48, because negative 48 is negative 1 times 48. This is my I. And 48 is 16 times 3, and 16 can be out as a 4, so we have 4I root 3. I know that for add or subtract radicals, I have to have like terms for add or subtract, and like terms means the radical part must be exactly the same. First, we didn't have the same radical. That's why we weren't able to add them. We started by simplifying the radicals. Now, after simplifying, I see that they are like terms because the radical parts are exactly the same. Both of them have root 3, which means they are like terms and I can add them together. But what do we add? These parts. What is 3I plus 4I? It's 7I, and we keep the root 3, and this is my final answer. To find the answer for part B, I just need to square the parenthesis, and square the parenthesis means multiply the parenthesis by itself. So we just need to multiply the parenthesis by itself. But the parenthesis has a radical with a negative. Let's simplify these first. What's the square root of negative 3? Square root of negative 3 is the square root of negative 1 times square root of 3. And that is the I. So it means inside the parenthesis, I have negative 2 minus I root 3. Now I want to multiply the parenthesis by itself for the square root, for the square part. So I need to square this parenthesis. I need to multiply this parenthesis by itself. And we just multiply 1 by 1. And negative 2 times negative 2 is positive 4. Negative 2 times negative I root 3, which is positive 2I root 3. Negative I root 3 times negative 2, which is positive 2I root 3. Negative I root 3 times negative I root 3. Negative times negative is positive. I times I is I squared. Root 3 times root 3 is just 3, which is 3I squared. These two are like terms. We can combine them. 2I plus 2I is 4I root 3. I can replace I squared by negative 1. And I know positive 3 times negative 1 is negative 3. And these are like terms. I can combine them. And 4 minus 3 is just 1. So the final answer is 1 plus 4I root 3. Next example is asking us to evaluate these expressions when x is equal to 3I. Evaluate them means find the answer when x is 3I, which means I need to replace the x by 3I. So let's replace the x by 3I. So we have 3I for x. Don't forget there is a square on top of that. And the denominator is 2 minus 3I. And on the numerator, 3I squared, it's 9I squared. I squared is negative 1, which is 9 times negative 1. which is negative 9 plus 19, and it's equal to 10. 19 minus 9 is 10. But the denominator stay the same because they are not like term and we can't add or subtract them. So after replacing x by 3i, I got this one. But I know, like the radicals, when we see a radical on the denominator, try to rationalize to get rid of the radical from the denominator. We do the same if I is on the denominator. I need to get rid of I from the denominator by multiplying by complex conjugate. And the complex conjugate of for 2 minus 3i is 2 plus 3i. Now if I multiply the numerators, I get 10 times 2, which is 20, 10 times 3i, which is 30i. And if I multiply the denominators, I have 2 squared, 2 times 2, which is 4, 2 times 3i, negative 3i times 2, negative 3i times positive 3i, which is negative 3 times 3 is 9, I times I is I squared. Like term cancel each other. I squared is negative 1, and negative 1 times negative 9 is positive 9. 4 plus 9, which is 13. And since there is only one number on the denominator, I can separate the radicals and rewrite it as a 20 over 13 plus 30 over 13i. And that's the final answer for this expression. The last part of this section is simplifying powers of I. How we can simplify when we have a power of I, like I to the 50 power, I to the 52 power. So what we can do? So as you see in this slide, I squared, or I to the first power, which is equal to I to the second power means I times I, which is negative, I times I, which is negative square root of negative 1 times the square root of negative 1, and the answer is just negative 1. I to the third power means I squared times I, and we know that I squared is always equal to negative 1, and if I multiply negative 1 by I get negative I. For finding I to the fourth power, I need to multiply I to the third by another I, and I found that I to the third is negative I, and negative I times another I is negative I squared, and since I squared is negative 1, negative times negative 1 is positive 1. If I want to find I to the fifth power, I need to multiply I to the fourth by another I, and I found that I to the fourth is just 1, and 1 times I is just I. And you see that we get back to the first power. It means if I want to find I to the sixth power, the answer should be the same as I to the second power. I to the seventh should be the same as I to the third. I to the eighth should be the same as I to the fourth. So the powers of I are cyclic, and you see that the only number that we get from I to the first to I to the fourth are I, negative 1, negative I, and 1, and it's repeating for every 4 powers. And since it's repeating for every 4 powers, when you have, for example, I to the 52 power, you need to know how many 4th power you have in 52. And if you divide 52 by 4, you get 13, which means I to the 54 means I to the 4th with the 13 power, which means 13 times 4 is 52. And I know I to the 4th is always equal to 1. And if I replace it by 1 to any power is just 1. So I know that I to the 52 power, it's 1 again. So you must get one of these numbers for every power of I. As you see, we have a cycle. Now, if you look at this example, we want to evaluate I to the fifth power. Again, I need to know how many powers of 4 is in 35. So we divide 35 by 4 again. And I know 8 times 45 is 32, with remainder 3. Which means I to the 35, it's I to the 4th 8 times, but 8 times 4 is just 32. I need 3 more. So I have to multiply these by I to the 3rd because of the remainder. Okay? I to the 4th is always 1. So, and 1 to any power is just 1. And 1 times any number, nothing changed. So the answer is just I to the 3rd. And what's the answer for I to the 3rd? Just negative I. So your answer is negative I. And that's the final answer.